Hey, this is the second clip of my scaling video series. So, if you look at this transistor, this is our favorite two-dimensional transistor, and the length is, um, yep, this one from source till drain. I'm just drawing an ideal transistor here. So you have a source, you have a drain, and then you have a gate. Gate is made of polysilicon, and these are the two diffusions. And then we have gate oxide in the between this channel and the gate, and this acts as capacitor, a dielectric for the capacitor between gate and the channel. So I explained the transistor operation in a separate video. So if you go to my YouTube channel, you will see one of those videos explaining how you start applying voltages as source, gate, and drain, and how channel works. But basically, what happens is, um, initially there is so this is where the current flows. So initially, a strong inversion happens. So a channel is created up here, and there is a particular gate voltage which we call threshold voltage. When gate to source voltage, between them is less than threshold voltage, no current flows. But when the gate to source voltage is more than threshold voltage, then you kind of reduce the barrier of this drain and source voltage, and the current starts flowing. The electrons start flowing in this side. Okay, so that's where the current is on, and it goes into linear, and then it goes into saturation. Again, if you look at that video, you'll get an idea of it. Now in today's video, I want to talk about the two important things. So as I mentioned previously, that we want to shrink the transistor in every generation, uh, because we want to put more transistors in a similar area, um, and that will reduce the cost of one transistor, because now the same area were double. Now where the concept of Moore's, this is important concept here, that every generation, every 2 year, you will see from the data as well that the goal was to reduce the length by 30%. So if it was 1, and the next generation would be 0.7 of that previous value. So 0.7x reduction in the dimension. Now it would be length as well as it would be weight. Overall kind of dimension resistance happens by 0.7x. Now if you look at an area, so if you have 0.7 here, 0.7 here is a square. So the area is becomes like 0.49. So before it was 1, right? 1, it was 1. So area becomes now 0.49 when one of the dimension reduces by 30%, or shrinks to 0.7 of its previous value. So you have seen that from 1, the area becomes half. Okay. So for the same, and now we have reduced the area of the device by 50%. What that means is, in the same area, now we will have 2 times as many transistors as we had before. Okay, so while this factor is 0.7x, the n, which is the number of the transistor, it doubles. So that's why we call it, okay, every 2 years your transistors double, as long as you can achieve this one. So you will see that every technology, new process node, by the way, this is the length. This is the length of this channel. This is typically used to describe a process node, like it's 0.350. Again, I'll explain. It's not exactly this. It's a little bit smaller, but typically if you think of the length is the process node. So every generation we try to hit 0.7x scaling. reduction in the dimension, and it results in 2x 2x increase in number of transistors for the same area. And that of course reduces your cost of one transistor by half. So that's an important concept on the Moore's law. The next clip I will talk about the supply voltage and the TOX as well as current. So see you then.